Assalamu alaikum students. This is the 11th lecture of CS 317 Operating Systems. This video covers the topic of concurrency. We use chapter number 5 of the William Stallings book. The central themes of operating system design are all concerned with the management of processes and threads. First, there is multi-programming, in which we manage multiple processes within a uniprocessor system. Then there is multiprocessing, in which we manage multiple processes within a multiprocessor. And then there is distributed processing, in which we manage multiple processes executing on multiple distributed computer systems. Fundamental to all these areas and fundamental to OS design is concurrency. Clusters are a prime example of distributed systems. Clusters are composed of many computers connected by any network, LAN or Wi-Fi. Now I know someone is going to say, why is this scenario called a cluster? It should be called a multiprocessor as it has many processors. But I told you that a multiprocessor has many CPUs on the same motherboard. And in a cluster, every processor is on a different motherboard. So a cluster is a network of computers. Then someone would say, why call it a cluster? Why not just a network? Well, in a network, all computers are connected, but each computer works on a different job. In a cluster, computers are not only connected, all of them are working on the same job or parts of the same job. One computer in the cluster is called the master. All users submit jobs at the master node. The master node partitions the job and sends the partitions to the slave nodes, asking them to do the same computation on their allocated partition. The point to note here is that all slaves execute the same program, but the data is different. When the slaves have done their work, they send their partial results to the master. The master consolidates these results and sends the final result to the user. For example, when you type www.google.com in the address bar of your browser, you are connected to the master node of the Google search cluster. Now let us suppose you want to search the term operating systems. Also suppose that there are 100,000 web pages in total. Also suppose that there are 10 nodes in the Google search cluster. So the master node allocates 10,000 web pages to each slave and asks each slave to search for the term operating systems in its web pages. If you do it with one machine, it would take the time to search in 100,000 web pages. But if you do it in the way I have just elaborated, you search 100,000 web pages in the time to search in 10,000 because all slaves work at the same time. So what is concurrency? Concurrency refers to the overlapping of lifespans of a set of events, which may be similar or dissimilar. Concurrency can occur in many areas, like communication among processes. Consider two communicating processes A and B. A has data to send and B is going to receive it. So for successful communication, it is important that A and B send and receive at the same time. For example, you are having a Zoom meeting with your friend. You can only have this meeting if the two of you log into a meeting at the same time. Only then can you tell him about the lecture you found so boring that you have decided you will not listen to it anymore. And I am sure there is a lecture like that out there. Concurrency can occur in sharing of resources like memory, files, and I/O access. Suppose you have opened a Word file and your friend tries to open the same file on a shared computer. Will Word let him open the file at the same time when you have opened it already? No, the operating system will give him a read-only version of the file. Concurrency can occur in synchronization of the activities of multiple processes. Suppose there is a shared memory buffer. There is a process which writes data into this buffer, and there is a process which reads data from this buffer. What will happen if the reader comes before the writer has written anything in the buffer? All those who say the reader will read garbage are correct. So this means that we always want the reader to come after the writer, not before him. We want a particular order: writer, then reader. Concurrency can occur in allocation of processor time to processes. The operating system takes care not to allocate the processor to two processes at the same time. Otherwise, we will not get any useful work done and we will only be left with garbage values. If you consider my examples, you will see that sometimes you desire concurrency and sometimes you don't desire it. When you and your friend are meeting on Zoom, you want your times to overlap. You want concurrency. When you are changing a Word file, you do not want another person to change it. You do not want concurrency. When a writer and a reader are using a buffer, you do not want concurrency. You do not want them to come at the same time. When you are dispatching processes, you do not want two processes to run in the same time quantum. You do not want concurrency. So sometimes you need it and sometimes you don't. We shall see that these issues arise not just in multiprocessing and distributed processing environments, but even in single processor multiprogramming systems. Concurrency arises in three different contexts, or in simple words, three different scenarios lead to some form of overlapping of events. Multiple applications. Multiprogramming allows processing time to be dynamically shared among several active applications. When one application is running on the processor, another application's requested I/O transfer is taking place. As I have said to you before, the CPU burst of one application overlaps the I/O burst of another application. Structured applications. As an extension of the principles of modular design and structured programming, some applications can be effectively programmed as a set of concurrent processes. When you write an application as a set of processes, you do this because you want them to run together. If you are time sharing on a uniprocessor system and you have an application with three processes, the processor runs the first process for a quantum, then it runs the second, then it runs the third, and then it runs the first again. So the processes get interleaved and their lifespans start to overlap. Operating system structure. We have seen that operating systems are themselves often implemented as a set of processes or threads. So if two operating system processes are interleaved on a uniprocessor system, their lifespans start to overlap too. The same thing that happens to user processes also happens to system processes. So this means that overlapping of lifespans can take place between processes of two different applications, between processes of the same application, and between processes of the system software. We start our discussion on the basics of principles of concurrency. Concurrent processing of jobs happens when we employ multi-programming, which is running one process on the processor and serving the I/O of the other. Time sharing, in which we interleave many processes using a very small time slot. Multiprocessing, which is running different processes on different processors at the same time. Multi-threading, which is running different threads on one or many processors at the same time. The relative speed of execution of processes cannot be predicted. It depends on the activities of other processes, the way in which the OS handles interrupts, and the scheduling policies of the operating system. What I want to say is you cannot predict that a smaller program A will complete before a larger process B. We are assuming A is smaller than B or A has less lines of code than B. But A makes an I/O call that takes very long to complete. And B is CPU intensive. So even with more lines of code, it finishes execution before A. Meanwhile, A is stuck in the blocked queue. Take the example again. We are assuming A is smaller than B or A has less lines of code than B. But B has been assigned a higher priority than A. Both of them are CPU intensive now. But the dispatcher uses priority to select the next process. So B is selected before A and finishes before A, even with more lines of code. So what are the difficulties for the OS designer? The first thing is the sharing of global resources is fraught with peril. For example, two processes both perform reads and writes on a variable X, and the order in which the various reads and writes are executed is critical. Suppose process A assigns 7 to X and process B assigns 3 to X. One day A comes first, B comes later. So the final value of X is 3. Another day A comes after B. What would be the final value of X? It is difficult for the operating system to manage the allocation of resources optimally. For example, process A requests for a resource. The OS grants the resource. Then A gets suspended, that is, it is swapped out of RAM. Now if OS keeps this resource locked for A and does not give it to the others, this can increase the waiting time of other requesters. The operating system may suffer a loss of performance if it keeps its promise with the suspended process. The third point is it becomes very difficult to locate a programming error because results are typically not deterministic and reproducible. Deterministic experiments have the same outcome every time you carry them out. If you flip a coin, it falls. Probabilistic experiments are the opposite of deterministic experiments. They can have different outcomes. If you flip a coin, it can fall on either its head or tail. So if you are flipping a coin and your interest lies in finding out what happens next, this experiment is deterministic because only one thing will happen. It will fall. But if you are flipping a coin and you are interested in the face that the coin falls on, then this is a probabilistic experiment as there are two possible outcomes. So suppose you are running two processes together. One of them has a memory fault. That is, a new page of the process must be brought into RAM. But after a few weeks, when you run these processes on a lightly loaded system, no memory fault happens. So what happens during concurrent execution, the correct things and the errors, all of them can change when the state of the system changes. They are not deterministic. Even when you run the same set of processes again, they do not block, execute, get interrupted, or get suspended in the same way as they did in their previous run. All these difficulties are present in both uniprocessor and multiprocessor systems. Let me give you a simple example. Consider the following procedure. This is a function called echo. Its body extends from one curly bracket to another. The keyword void shows it does not return a value. The getChar function captures a character from the keyboard and assigns it to the variable ch_in or character in. The second line of the function's body assigns the value of ch_in to a variable ch_out or character out. The putChar function prints the value of ch_out onto the console output, which would be your monitor. This function provides a character echo procedure. Input is obtained from a keyboard one keystroke at a time. Each input character is stored in variable ch_in. It is then transferred to a variable ch_out and sent to the display. Any program can call this procedure repeatedly to accept user input and display it on the user's screen. Let me tell you some more things about the function echo. Consider that we have a uniprocessor multi-programming system supporting a single user. The user can jump from one application to another, and each application uses the same keyboard for input and the same screen for output. Because each application needs to use the procedure echo, it makes sense for it to be a shared procedure that is loaded into a portion of memory global to all applications. Thus, only a single copy of the echo procedure is used, saving space. However, such sharing of memory can lead to problems. Consider the following sequence. Process P1 invokes the echo procedure and is interrupted immediately after getChar returns its value and stores it in ch_in. At this point, the most recently entered character x is stored in variable ch_in. Process P2 is activated and it invokes the echo procedure, which runs to conclusion, inputting and then displaying a single character y on the screen. Process P1 is resumed. By this time, the value x has been overwritten in ch_in and therefore lost. Instead, ch_in contains y, which is transferred to ch_out and displayed. So the input to P1 was x, but the output of P1 was y. Why did this happen? Because two processes were altering variable values in the body of a shared function. Thus, the first character is lost and the second character is displayed twice. The problem is the shared global variable ch_in. Multiple processes have access to this variable. If one process updates the global variable and then it is interrupted, another process may alter the variable before the first process can use its value. So how can we resolve this problem? Suppose that we permit only one process at a time to be in the function echo. Then the same sequence goes like this. Process P1 invokes the echo procedure and it is interrupted immediately after getChar returns its value and stores it in chain. At this point, chain contains X. Process P2 is activated and invokes echo. However, because P1 is still inside the echo procedure, although currently not running, P2 is blocked from entering the procedure. Therefore, P2 is waiting the availability of the echo procedure. At some later time, process P1 is resumed and completes execution of echo. The character X is displayed. When P1 exits echo, this unblocks P2. When P2 is later resumed, the echo procedure is successfully invoked, Y is inputted and Y is outputted. This example shows that it is necessary to protect shared global variables and other shared global resources too. And that the only way to do that is to control the code that accesses the variable. If we impose the discipline that only one process at a time may enter echo and that once in echo the procedure must run to completion before it is available for another process, then the type of problem we saw in the previous slide will not occur. Please remember that when I started this example, I said that the system was a uniprocessor system. So problems due to concurrency do happen in uniprocessor systems. Obviously, they would be present in multiprocessor systems too. In a multiprocessor system, suppose that there is no mechanism for controlling access to the shared global variable. Processes P1 and P2 are both executing, each on a separate processor. Both processes invoke the echo procedure. As we move through the figure shown here, events on the same line take place in parallel. First, P1 takes input. Let the character just pressed be X. So cha-in now has X stored in it. In the next execution cycle, P2 takes input. Let the character just pressed be Y. So cha-in now has Y stored in it. Both P1 and P2 store the value of in cha-out at the same time. So cha-out has Y stored in it. P1 prints cha-out on the screen, so Y is printed. P2 prints cha-out on the screen, so Y is printed a second time. The result is that the character input to P1 is lost before being displayed, and the character input to P2 is displayed by both P1 and P2. Now let's look at resolution of the problem on the multiprocessor system. Again, we enforce the rule that only one process at a time may be in echo. Processes P1 and P2 are both executing, each on a separate processor. P1 invokes the echo procedure. While P1 is inside the echo procedure, P2 invokes echo. Because P1 is still inside the echo procedure, whether P1 is ready, blocked or running, P2 is blocked from entering the procedure. Therefore, P2 is blocked, waiting the availability of the echo procedure. At a later time, process P1 completes execution of echo, exits that procedure and continues executing. Immediately upon the exit of P1 from echo, P2 is unblocked, and when P2 is resumed, it starts to execute echo. Why does the problem occur? In the case of a uniprocessor system, the reason we have a problem is that an interrupt can stop instruction execution anywhere in a process. because it can lead to a process switch. In the case of a multiprocessor system, we have the same condition, and in addition, a problem can be caused because two processes may be executing simultaneously and both are trying to access the same global variable. However, the solution to both types of problem is the same. Control access to the shared resource. Allow only one process to access a shared resource. If process A has a variable that only process A uses and nobody else ever asks for it, there will be no concurrency related issues with this variable. If a resource is not shared between two or more processes, it cannot create a concurrency related problem. So what we need to watch out for are shared resources. If there is a value that many processes read but nobody ever changes it, that is, it is a constant, there will be no concurrency related issue with this variable. If a resource is not modifiable, it cannot create a concurrency related problem. So what we need to watch out for are resources whose values can be written to or changed. So as a system designer, we should be cautious about shared modifiable data. Now I introduce a new term to you, race condition. A race condition occurs when multiple processes or threads read and write data items so that the final result depends on the order of execution of instructions in the multiple processes. As a first example, suppose that two processes P1 and P2 share the global variable A. At some point in its execution, P1 updates A to the value 1, and at some point in its execution, P2 updates A to the value 2. Thus, the two tasks are in a race to write variable A. In this example, the loser of the race, the process that updates last, determines the final value of A. For our second example, consider two processes P3 and P4 that share global variables B and C with initial values B equal to 1 and C equal to 2. At some point in its execution, P3 executes the assignment B equals B plus C, and at some point in its execution, P4 executes the assignment C is equal to B plus C. Note that the two processes are updating different variables. However, the final values of the two variables depend on the order in which the two processes execute these two assignments. If P3 executes its assignment statement first, then the final values are B equals 3 and C equals 5. If P4 executes its assignment statement first, then the final values are B equals 4 and C equals 3. I have just discussed a similar example. Now I want you to take some time to figure out the answer to this question. P1 and P2 share global variables B and C with initial values B equals 5 and C equals 1. At some point in its execution, P1 executes the assignment B equals B minus C. At some point in its execution, P2 executes the assignment C equals B minus C. What final values are possible for the two variables? Now that we have understood what concurrency is and how it raises problems for us, the next question is what design and management issues are raised by the existence of concurrency? We can list the following concerns. Number one, the OS must be able to keep track of the various processes. This is done with the use of process control blocks. And we read about process control blocks in process description. Number two, the OS must allocate and deallocate various resources for each active process. At times, multiple processes want access to the same resource. These resources include processor time. Allocating processor time is called scheduling. We have already discussed uniprocessor scheduling. Memory is another resource. Most operating systems use a virtual memory scheme. Files are another resource. And the last resource are I/O devices. Number three, the OS must protect the data and physical resources of each process against unintended interference by other processes. And number four, the output of a process must be independent of the speed at which its execution is carried out relative to the speed of other concurrent processes. We now discuss the different types of interactions that can take place between processes. We can classify the ways in which processes interact based on the degree to which they are aware of each other's existence. Sometimes processes are totally unaware of each other. This is one kind of interaction. Sometimes processes are indirectly aware of each other. So this is the second kind of interaction. And the final kind of interaction is when processes are directly aware of each other. Processes unaware of each other. These are independent processes that are not intended to work together. There is no exchange of information between these processes. The best example of this situation is a batch of jobs in a multiprogramming uniprocessor system, each submitted by a different user. Although the processes are not working together, the operating system needs to be concerned about competition for resources. For example, two independent applications may both want to access the same disk or file or printer. The OS must regulate these accesses. The operating system needs to ensure that if two independent processes want the same file or the same I/O, only one gets its wish at a time. For example, a doctor is sitting in his clinic. All kinds of people come to get treated by the doctor. They do not know each other. They are all competing to get the doctor's time. The state of the resource for which the processes are competing remains unaffected after it has been acquired or used by a process. No matter how many people the doctor treats, at the end of the day he is unaffected, just a bit tired, but he still has two arms, two legs, and a wise brain. Examples of such resources include I/O devices, memory, processor time, and the clock. These resources are not changed by use. They are called reusable resources. The doctor is also a reusable resource. However, the execution of one process may affect the behavior of competing processes. If two processes both wish access to a single resource, then one process will be allocated that resource by the operating system and the other will have to wait. Therefore, the process that is denied access will have a larger turnaround time. If two patients are waiting to be treated, one is allowed to see the doctor while the other waits. So, he returns home late. What are the problems of competing processes? We face three control problems: mutual exclusion, deadlock, and starvation. The last two problems are a consequence of the first. What I mean to say is mutual exclusion leads to deadlock and starvation. Since it will take us a lot of time, we will go into the details of these problems in the next lecture. So, what did we learn today? We were introduced to the concept of concurrency. Concurrency is the overlapping of lifespans of different events. We realized that sometimes concurrency is desirable and sometimes it is problematic. We realized that concurrency related problems always exist for shared modifiable data. So if we have data that is not shared, just local, then we will not have any concurrency problem for it. If we have data that is read only, it cannot be written to, then we will not have any concurrency related problem to it. For a concurrency related problem to appear, the data has to have both properties. It should be shared and it should be modifiable. We realized what race condition is. We were introduced to the types of process interaction. I understand that this is a new topic and at first it may seem a bit difficult, and you might have heard of terms here in this lecture that you hadn't heard of before. So I've tried to keep things slow, but I will explore all those terms in the lectures that follow, and I promise you that you will enjoy them. So, what are the things that I want you to do? I want you to read the book, keep your questions noted on a piece of paper, and put them up when we meet in the online session relevant for this lecture. And if you have suggestions relevant to content or quality of this lecture, email them to me. Take care of yourself. Allah Hafiz.